Hello. Today we're looking at logistic functions, and we have an example dealing with an epidemic. We have in a city of 500,000, there are initially 800 cases of a particular particular strain of the flu. The Center for Disease Control and Prevention in Atlanta claims that the cumulative number of infections of this flu strain will increase by 40% per week if there are no limiting factors. We're to make a logistic model of the potential cumulative number of cases of flu as a function of weeks from the initial outbreak. So prior to doing this example, we have to know that an epidemic is typically modeled by a logistic function, and so we are going to be trying to create an equation for a logistic function. I have at the top of our screen the equation for a logistic function. I have the formula for how we figure out the b value, and I have three different formulas here giving me relationships with a and r. So I'm going to start going through my problem and figuring out what's what. So the first thing that I notice here is that we have 500,000 people in our city. Now, at first glance, it might seem like this is Atlanta, but Atlanta is where the CDC is located. So we have an unnamed city, 500,000. As a number, 500,000 is 500,000. And how this fits into the formula, this is K, that limiting factor. If we're only considering this city, we can't possibly have more than 500,000 people getting the flu. Next, it says there are initially 800 cases. So this word initially is really important, and this is my N of 0, my starting amount, which I need to figure out the B value. Next thing that I notice here as far as a number is that it's going to increase by 40% per week. Okay, so goal is to make this logistics model. So I start out with N equals, and we set our K value, our cap on this entire thing, our limiting value is 500,000 or 500,000. In the denominator we have 1 plus, and the next thing that we encounter is B. And we have that the formula for B is to take K. So off to the side here, B equals 500,000 divided by the starting amount, which we noticed was 800, and then subtract 1. So I have done this on my calculator ahead of time, and I get 624 for that number. So in my equation, B is 624. Next I have E, which we know is just a constant. It's an irrational number, and our calculator has that. Then I have a negative, and then I encounter R. And there are quite a number of relationships with R, and so we want to look for the one that's relevant to this problem. And so we know that A is 1 plus a percent, and in this problem we have a percent. So I can start finding A, and I take 1 plus, and 40% as a decimal would be 40 over 100. And I do all that in my calculator of 1.4. Now that is not R, that's A. Once I know A, I can figure out R by using the natural log of A. So then I have natural log of 1.4, and again, I'm going to a calculator to do this, and I did do that ahead of time and got 0.336, and we're typically going to round that to 3 digits for our R. So the negative is part of the formula, and then we have 0.336 as that exponent, and then we have T, our other variable. So what we have created so far in this area is that logistic model. We've come up with the huge formula that is supposed to model the cumulative number of cases of the flu. So now we're ready for our bullet point here, which is how long will it be before 100,000 people are infected? That 100,000 people is a value of N. So really I'm asking 100,000 is equal to this whole mess of a formula. We could solve this by hand. It would be a lot of algebra steps, which means there's lots of room for error. And because our unknown is this exponent t, it would involve use of a logarithm. And we know how to do that, so we could. I think we're going to have an easier time solving by graphing because we don't have as much room for all those algebra mistakes. So I'm going to put this as my y2. I'm going to put this entire thing as my y1, and I'm going to attempt to cross the graphs. So I'm going to go to my graphing calculator. So I'm going into y equals, typing my formula. When I divide here, it's very important that I have parentheses because we have a lot of math going on in the denominator. And then once I've typed my exponent, get out of the exponent spot before I end my parentheses. So my y2 was the 100,000. All right. So then I have to think about what would be an appropriate window. So our flu epidemic was spreading by weeks. And so this is just a guess, but I'm going to look at 52 weeks because that would be a year. And then in the y direction, we need a number greater than 100,000. And I'm actually going to go up to the 500,000 because I know that that is the limiting value, that is the k value that I put in this function. And so that's going to allow me to see the full logistic curve rather than just see the section that I want. And so I hit graph and we'll see what we got. And I have an error in my syntax. So I'll go to where my typo is. And it looks like I typed a subtraction instead of a negative sign there. So we'll fix that and try again. So that blue curve is my logistic curve, and we see that it has its iconic shape, that it starts out exponential, and then it slows down to leveling off. My red line is my 100,000, and I can figure out the answer here by finding where they intersect. I can hit enter through all of these curves, because I only have 2 equations in there, and I get at about 15 weeks, we'll be at the 100,000 mark. So going back here, how long will it be before 100,000? We solved by graphing, and we got 15 weeks. So I'm going to draw a quick sketch here, which would be my work for this. Down here was weeks. We went out to 52. This would be the number of people, the population. And we went up to 500,000 because we knew that was our limiting value. And we had our logistics curve come up here. And then we graphed 100,000 right here. And we found this intersection point at 15 weeks. All right, so the next one asks me, when is the flu spreading the fastest? So the first thing that we have to do is make a connection, and that is that the fastest growth equals the point of inflection. And we've been abbreviated point of inflection, POI. We also know from the discussion we've had about logistic that the point of inflection equals 1/2 of the maximum, which is k. So if I take 1/2 of the maximum, 500,000 people in the city, I end up with 250,000. From there, I'm going to solve much in the same way that I solved the previous problem. This 250,000 is a population, an n, and so it would go into my formula for n, which means it's going to go into my calculator for y2. So I'll go back to my calculator. I'm going to go into my y equals, and I'm only going to change my y2. So I'll change this to 250,000. hit graph. And this time our red line has moved up to 250,000, and we see that it hits right in the middle of that steep incline. And that's because this first half is exponential. Point of inflection is that moment where the concavity changes from concave up to concave down, and this point is the fastest growth rate. So to find that actual ordered pair, I'm going to use the intersect command. I enter for first, second curve, and guess. And so it will be spreading the fastest at right about 19 weeks. So when is it spreading the fastest? 19 weeks. And to solve that, we just added a different line here at 250,000. And we found this point, which my line might be a little bit high there, to be at 19 weeks. And we got there, though, by knowing that the fastest growth is going to occur at the point of inflection, and that the point of inflection occurs at half of the maximum.